Hi everyone, welcome back. So in this video, we will discuss about process address space. So let's get started. So in this video, we will discuss about address space, memory descriptor, virtual memory areas, and how we can manipulate those memory areas. And at the end, we will discuss about page tables. So as we know, when we build a process or compile a program, then this is the memory structure of that program that we have. So it has different sections like text section, data section, and stack. So this whole memory area is represented uh, in the main memory with the help of process address space. So you can say that this is the whole area that is allocated to a particular running program that we call it as a process. And this address is virtual address and it is specific to a particular process. So what is the benefit of virtual memory? So every process running inside a system assumes that whole main memory is having under his control, and it also helps us to run the process that are more or large in size more than the main memory. So this is the two benefits of virtual memory concept in the Linux. So address space represents the addresses that a particular process can access during its execution. So the address space is given based on the architecture. So it can be 32-bit or 64-bit address space. And we have two mechanisms to allocate the address space. So first one is segmented address space, where we allocate the virtual memory addresses to a particular process based on the segments, and it is not widely used. So Linux use this flat address space mechanism, where we are giving each process a unique address space. So if there are two processes P1 and P2, and they have this address 0 and this also have address 0, so though this address is specific to this process and this address is specific to this process. In the coming slides, we will understand how we try to make differentiation between the address spaces of different processes. So as we know that address space defines a address area where a process can execute. So whenever we try to access the address that is outside of that area, then kernel gives this segmentation fault and that process is killed by the kernel. So here we can see how we represent this address space inside our structures. So as we have studied in previous lectures that every process have this structure called task struct. So if you go back and look inside this structure, you will find this field So this is the field that stores the address space of that particular process. So this field is of type struct. So in the struct, you have two these variables and other variables also. So this represents the top level page table. We will understand further in our slides, as we have already studied in the memory management lecture that we have different page tables to map from virtual address to physical address. So this is the same structure. If you see here, this variable represents uh, a different structure called VM area struct. So this VM area struct actually represents a particular section of memory map of a process. So like in our first slide, we have seen we have different sections like text, data, and stack, BSS, heap. So this particular area is defined by this structure. We call it as VM area underscore struct. So what this structure has, it has the start address and end address, and it is the permissions on that particular address, and it also have a pointer to the next section. So in this way, from this structure, we are representing the whole address space of a particular process that is given on the RAM. So if you see, this particular section of memory is allocated for this data, and this is allocated for text or executable. So here you can see, uh, as we know, this is a variable for the first page table. So it will go and it will point to this page table. So based on this page table, it contains the address of other page tables. So it will go to different page table, and at the end we have the mappings from virtual memory to the physical memory. So this is a Linux kernel three-level virtual memory mapping to the physical memory. So here you can see that here you have this area of memory is allocated for code and data section, and this is allocated for stack. So in this way, we map the different area of a memory of a particular process to the physical RAM. So let's deep dive into the different structures. So if you see, with whole memory of a process, we represents with the help of this struct. So this this is the struct that represents that. So if you see here, this is the particular variable that have the linked list of all the areas of a particular process, like text, data, stack, and this is also the same. This also contains the same thing, but this is a red black tree of the different VM area structures. So it helps in the quick lookup of a particular area. So like if you want to access a text area, so and you want to modify something or like fetch the instruction from this, then it will go there, and so it will make that lookup very fast. And like after that, if you want to the next instruction in the text area, then this mapping will be helpful, because it contains the linked list of the particular uh, uh, structure. So that's why this question, like we have both this answer this question, that we have the mmap and mmrv both. So it it actually optimize the access in the Linux. So we have the benefit of keeping this redundant information in two structures, in this one and in this one, so that overall performance of the kernel is very fast. And here we have two another important properties. So this is a users, like if this memory is shared between different processes like threads, then what the like if we have process 1 and it has two threads, T2 and T1, so the mm users here will be 2, and mm count is equal to 1, because this count is incremented by only one process. And if the same area is used by different threads, then we just increment the users field. So if multiple processes are using this particular memory area, then we will increment the count field. And this is the list which contains all the memory areas contained by different processes. So this list is memory map of different processes running inside the kernel, and this is the total number of pages allocated to that particular address space of a process. And here, if you look carefully, if you see that it also defines the different start and end address of different sections. So if you see, this is the data, this is code part or the text section. So in this way, this structure can represent the whole address space of a particular process. And this question like threads can share process address space, and we will answer this question inside the new slides. So when we allocate this structure, then we are allocating that structure from the uh, slab cache implemented inside Linux kernel, and that is being allocated with the help of this alloc function. So this is a macro, and we call this function, and this memory struct will be allocated to that particular process, and this struct is unique to every process. So in this way, we make sure that every process is having uh, a separate address space. And like when we are creating a thread or a child process from a process, and we don't want to like we want to share the address space, then in the like we know that when we call a fork system call, it internally calls the clone of system call. So in clone system call, if you remember, then we have different type of flags. So if we specify clone vm, this ensures that the address space of parent process will be shared by the child process like a thread. So like if our process stops execution or it has completed, then at that time we have to make sure that whatever memory allocation we did for our process, that we have to put back. So this is a sequence of functions that it calls to free the address space of a particular process. So if you see this exit underscore function just do some housekeeping and update some statistics. After that, it checks. After that, it calls this function mmput. So what mmput does, it decrements the user field that we have already in the structure, as we seen in the previous slides. So if this users field is 0, like if a process is running P1 and it has T1 and T2 threads. So like if T1 has completed its execution, then it will be decremented users. And again, if T2 also have uh, completed the execution, then users will again be decremented. If it checks that if users become 0, that means this whole process have completed. So at that time, it decrement this count variable with the help of this drop function. So if this address space is shared between different processes, uh, at that time, uh, it will check if this count become 0. That means no other processes are sharing this address space. At that time, it can call this function free function, and it will free the structure from the slab cache, and finally it will free the memory from the kernel. So let's see about the kernel threads. So when we are creating threads from a process, at that time we keep this field of that particular process as the null value. So like whenever a thread is running, it will take the address space of its parent. So it keeps that address of its parents into this field, call it active underscore So when how it does, like when process is scheduled, at that time it reference the field. If it finds that this is a null, then it will load the address space of the parent, because it already have the pointer to the parent process. So from that it will access the parent address space, and it will load into this active field, and this will become the new address space for that particular thread or child. So this is the sequence, like task struct, we have this field, and based on the field, we update the active field to specify the new address space of a particular process or thread. So here, if you see, these are the different sections. So what we need in a section? We need the start or end and the permissions, what we can do in a particular section. So this structure VM underscore area underscore struct represents this a particular section. So here you can see that it has start, it has end variable, it has this uh, uh, protections of of that area, and it has this next field that we have already seen in the diagram in the previous slides, and it also contains this red black tree of these uh, virtual memory areas. So as you can see, as you know that in some of our programs, when we write a C program, we open some files inside that. So if we have some open files associated with our process, that we can map with the help of these two values inside this structure. So it will give the offset within that, within the file, and the pointer to that particular file. And these are the different flags. This is represented with this variable. If you see here, this variable. So like here, like if you discuss this text section, so text section can be it is a executable file, so it can have the permission of read, write, and execute. So uh, this section will have read, write, and execute permissions. But if you see that, if a data section, it is not meaningful to give the permission of executable, because we are not given we are never going to execute anything on data section. So it will have read and write permissions, so that we specify from these flags. So if we specify this flag, then it will be it will be having read permissions. And also, like, look into this variable, and this variable is for uh, memory mapped files. So it is not like only the process can be mapped into the RAM. So we can like assume that this is a whole RAM and this is our one process mapped into here. So we can have areas where we have memory mapped file. So in this section, if we want to represent this particular section, then we have to specify this flag. And similarly, we have this property that if we don't want to copy the that particular section, which like while making a new process, at that time we can specify this pm underscore don't copy flag, so that it will not copy the address space of particular process when creating a child process or other process. So to like in Linux, we already know that whatever structure we have associated operations. So these are the same operations that we can run on virtual memory area. So if you see here, this is the open function and this is close function. So this function is uh, automatically triggered because these are the callback functions. When we try to add a particular, this is for adding. So like if I add a new VM area struct inside my memory map, then this function open will be called. When we remove that particular VM area struct, then close function will call. And this is the function, it will be called when we are accessing address space or virtual memory area that is not permittable, that is not having the permission to access. At that time, this function, the fault function, will be called. And this function page underscore mk write, this function will be called when we have a page that was only readable and now we are making it writable. So at that time, this function will be called. And this access function will be called to access the VM area of VM area of a process when we are not getting the user pages, like when we are trying to access the user page and uh, and we are not able to access those pages, then at that time it will access the VM area of that particular user, and this access function will be called. So like as we have already discussed that this is a map variable, so it links the all memory area object of in a linked list manner. So if you go back and see the structure again of struct here, if you see that this is a variable, so it contains the different virtual memory area of different sections like text and data in a linked list format. And we have already discussed that this we have mmrv. So this is a red black tree that contains VM area struct of different sections in a red black tree fashion for accessing it very quickly. Like it takes log and time, so it makes very fast lookup. And if you see here, like this is kind of like this is a root and we have different fields vmrv. So these are the childrens of that particular tree. So if you see, this variable represents a specific virtual memory area field. So so like uh, the obvious question comes, why we are having this redundancy? As I have already discussed the partial answer of that. So it makes optimal performance of Linux kernel, because if I want to operate on some memory area, then we can use red black tree to quickly go to that area. And then if I want to go to the next address, then we can use this mmap structure to linearly access a particular address inside a particular area. So it gives the optimal performance in the runtime. So if you want to access and manipulate some area uh, in the like area, and within that area we have to do some operations on the address, then we have these functions like find vma, so find previous vma, and find intersection of vma. So here we are giving the address that we want to access. So this is the variable that represents the whole memory structure of a process. So with the help of this, we go to particular address inside the address space of a process. And similarly, we have different similar variables for the other functions. Here, if you yeah, so here it will return the first address space that is intersecting like between this the start and the end address. So if there is some memory area in between this, it will return the address of this particular uh, VM area struct. So let's now understand how we are creating the mm struct for a particular process. So that is being done with the help of this function called mmap. Actually, this is not a function call, this is a system call. So this is the system call from the user space, and this internally maps inside the kernel that call as do underscore mmap system call. So it will, what it will do, it will allocate the address space for particular process based on these permissions and like flags. So whatever we want to specify, we can specify here. So if you see, we have this file and offset. So if we are creating a memory area for a file mapped process, then at that time we have to specify the pointer to the file descriptor and the offset within the file. So when our memory area is uh, allocated for particular file, then at that time we can say that this is a file backed mapping. And if it is not mapped with the file, then we call it as a anonymous mappings. So if we pass different arguments to these functions, so if anything like if any of the parameters are not valid at that time, the do mmap fails and it returns the negative value. And if it is if it passes and it allocates the virtual memory, then it will check if the newly allocated virtual area can be merged with the previously allocated memory area. So like if we have this memory area and this is the new allocated memory area, if these are uh, continuous and the permissions and other properties of both the sections are same, then at that time it will merge and make it a single memory area for that particular process. And this it and it adds this address to the red black tree and the linked list also. And it will update the total VM because we have like this field we have in the structure. So now we have allocated new memory area, so the count of this total underscore VM field will increase and it will be updated. So similar to the allocation, we have the functions for deallocation. So this is a sequence call of the functions that we do to deallocate the memory area. So as usual, this is a user space system call, and this is the uh, wrapper function that maps the system call to kernel function, and accordingly it will deallocate the particular address space for that process. So let's now see the visual of the different structures that we have already gone through. So if you see, these are the structure of different processes. So you can say this is a P1, this is P2, this is P3. Within that particular process, we have different VM area structures, and these VM area structures are connected to each other with the help of VM next field that we have already visited in our structure uh, description. So if you see that we already told that VM area can be have for mapped files also. So this is pointing to the file virtual file system of that particular file. And like we whatever program we have here, we divide them into the pages, and these pages are allocated to the buffer. So we will in the next lecture we will discuss more about address space. So those buffers are mapped to the with the help of mmap function that we have already seen. It will be mapped to different VM areas, and so this is how the whole mapping of different pages and then the memory area and then memory structure is being done. So this is just the overview of all the things, all the structures we have seen. So like we have the virtual memory area of a particular process. So if CPU want to access a particular area of that particular process for doing some operations like read or write, at that time we have to translate that VM area to the physical address space in the main memory. So this we do in the Linux based on the page tables. So we have three level of page tables here in the Linux, and these page tables are, so this point is very important, like these page tables are specific to a process. So when we create a process at that time we set up those page tables, and these page tables are architecture dependent. And if you remember, we have already discussed about the process management. So we have different properties uh, that we have to set. That's why it is a architecture dependent. So like if our CPU will access those virtual address then physical address from the RAM, it will take quite a time. So we have one hardware cache that we call it as translation look aside buffer. So we keep the virtual to physical mappings of recently accessed pages, access addresses inside this buffer. So CPU can directly look into this buffer. If the address is already available, it can directly access the RAM. If it does not, then we have to go through the translation from VMA to physical address and then update the translation look aside buffer so that next time, if in the near future we are accessing the same address, then we don't have to go through the process. So here, if you see, this is the pictorial view, how the translation goes. So as we have seen that struct is the memory map of particular process. It contains this particular variable PGD. So PGD stands for uh, program global directory. So this is the top level page table. So it will access this page table, and this page table contains the address of the next page table. So this is the program middle directory. So this is the intermediate page table, and this page table give us the actual mappings between the physical RAM and the virtual address. So based on the page table entry, we'll get the address of the physical RAM. So this is how we translate the virtual address space of a particular process to the physical address space inside RAM. So this is the end of this lecture. So actually in this lecture, we have seen how we represents the address space of a particular process with the help of struct field, uh, struct structure. And then within that address space of a particular process, we have seen it contains different sections like text, data, stack, heap. So that we represents uh, based on this VM area structure, and the creation of different VM area struct we do with the help of map system call. And if you want to destroy the memory areas when process finishes running on the system, we do with the help of this unmap system call. And at the end, we have discussed how page tables helps us to translate from virtual address space to the physical address space. So this is all for this video. I will see you in the next video.